Welcome in. Our objectives for this video are going to be able to calculate specific heat capacity, heat, temperature, or mass using our equation. And we want to identify chemical reactions as either endothermic or exothermic. Let's start by introducing this idea of heat capacity. Different objects and different materials will change temperature at different rates with different amounts of energy added. Think about it. If you put something into the microwave, maybe you put your Hot Pocket into the microwave. When it comes out, is everything perfectly uniformly heated? Well, probably not. Maybe parts of it are ice cold and parts of it are scalding hot. That's because different materials have different heat capacities. Heat capacity is going to quantify how much heat is required to change the temperature of a substance by 1 degree Celsius. Our picture on the left, we have two different frying pans. This little cast iron frying pan and this big cast iron frying pan. How much energy is it going to take to heat up our little frying pan by 1 degree Celsius? Well, depending on the frying pan, maybe a little bit of energy. How much energy is it going to take to heat up our large frying pan by 1 degree Celsius? This one is much bigger. It's going to require more energy. So our two different frying pans have two different heat capacities. Heat capacity, we get to quantify this. This is going to be how many joules of energy are required to change our substance by 1 degree Celsius. The units are joules per degree Celsius. And this heat capacity is really useful for measuring different objects. Comparing our little frying pan to our big frying pan. We have another term on this slide. We can also discuss the specific heat capacity. This is the same idea, how easy or difficult it is to change the temperature of your substance by 1 degree Celsius. But now we are normalized to comparing this per gram. So it is the joules per gram of our substance to change it by a degree Celsius. This is subtly different, and it is going to be more helpful for our different materials as opposed to our different objects. As it turns out, the specific heat capacity for iron is going to be the same if you have the same type of substance. If we're looking at our two frying pans again, the specific heat capacity for iron is the same whether we have a little frying pan or a big frying pan, because this is per gram. It's not based on the size of that object. It's based on the material. Both these terms are trying to get at the same thing. How hard is it to change the temperature, or how easy is it to change the temperature? But one is more useful when describing objects, the other is more useful when describing a material. We can start to look at some of these numbers. We see specific heat capacities for some of our metals, and then for some of our liquids. Notice here that our metals generally have very small heat capacities, and our liquids have much higher heat capacities. This is probably true to your life experience. Metals tend to heat up very fast, whereas something like water takes a long time to heat up. If you put a pot of water onto your stove trying to cook some pasta, The pot will get very hot very quickly, but the water will take a long time to change its temperature, heat up to that boiling point. Well, that's because our specific heat capacity for water is very large. A large heat capacity means that this requires a lot of energy to change its temperature. Since we have numerical values for our specific heat capacity, we can start to do some calculations. We can introduce this equation, Q equals mc delta T, which describes the relationship between our heat that is required, the mass of our object, the specific heat capacity of our object, and how much the temperature will change. Heat is given the symbol Q in this class. Mass, we can use the symbol M. Specific heat capacity is given the symbol C. And let's be very careful here. I know it's confusing. Heat and heat capacity, or heat and specific heat capacity, are two different things. And both of those things are different than our temperature. Temperature is given the symbol T. We have this little triangle. That triangle is the Greek letter delta. And delta T is described as the final temperature minus the initial temperature. That delta symbol means change in. Here we're describing the change in temperature, but you could also have the change in X or the change in V, whatever you want. We'll see this delta symbol a lot. A couple notes on units and signs. Make sure that your units all match up. If you have your units of mass in terms of grams, your specific heat capacity in joules divided by grams in degrees Celsius, your temperature here can be in degrees Celsius. Your heat will end up in units of joules. When we're doing these calculations, our mass is always a positive number. Our specific heat capacity is always a positive number. But our change in temperature can either be positive or negative. Because of that, our Q value, our heat, could either be positive or our Q value could be negative. If our Q value is positive, this means that we have an endothermic reaction. This process is going to absorb heat from the surroundings. If we end up with a negative value for heat, this means that we have an exothermic reaction. Our reaction is going to produce heat. Energy can't be negative. What that negative sign means is, well, the heat is being released outwards. It's going to exit into the surroundings. We have an example here. 328 grams of water absorbs 5.78 times 10 to the third joules worth of heat. Can we calculate the change in temperature? This is a heat question, so let's use our heat equation. We can think about which values that we know. We are absorbing this much heat. That is going to be our Q, heat. We have 328 grams. That is going to be our M, mass. Our specific heat capacity, we can look that up for water. This is going to be 4.184 joules per gram degrees Celsius. We don't need to memorize that. We can just look that up. And there we go. It looks like we have everything except our delta T. If we want to isolate delta T by itself, we can divide both sides of the equation by M and C. Now we have Q divided by MC equals to our delta T. And I'd like to plug in my numbers maybe now. Here we go, we get our answer. Double check, our units cancel out. Joules divided by joules, grams divided by grams. We end up with 1 over degrees Celsius. That's just the same thing as degrees Celsius. Our change in temperature will be 4.22 degrees Celsius. Notice here I wrote positive 5.78 times 10 to the third joules as our Q value because we are absorbing energy. Absorbing means that we have endothermic, means that we have positive value for our Q number. There's a follow-up question. If our temperature was initially 25, what is our final temperature? Well, the change in temperature was positive 4.2 degrees, which means it is increasing by 4.2 degrees. Our final temperature should be about 29.2 degrees. All right, now that we've gone through an example, we can try a practice problem on our own. Pause the video, get some paper, see if you can get a good answer. There we go, we've made it to the end. By now we can calculate either specific heat capacity, heat, temperature, or mass using our heat equation. And we can identify reactions as endothermic or exothermic. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.